In this video, we are going to talk about how a vacuum tube works, its electrical characteristic versus a transistor, and how can we use it as an amplifier, and some of the drawbacks. So here is the diagram of a vacuum tube. It is basically a chamber under vacuum. Here we have an electrical heater, and by heating up the heater, we can reduce the potential energy required to remove an electron from its parent atom. And now let's apply some positive charge to the anode and some negative charge to the cathode. This will create a potential field and allow the electron to travel from the cathode to the anode. Now let's apply some positive charge to a metallic grid that sits in between the anode and the cathode. This will create a stronger electrical field, which will allow more electrons to travel from the cathode to the anode, which create a stronger current. And now let's assume that we have inverted the charge on the grid. Let's apply some negative charge. This means it will create an opposing field between the grid and the cathode. And depending on how strong this field is on the grid, we can reduce the number of electrons that is traveled from the cathode to the anode, or completely eliminate any charge that is going to travel from the cathode to the anode. So now we see we can use this property by applying a small signal voltage named Vin. And we see that if we have a higher Vin, then we will have a higher current, right? And if we have a lower Vin, then we will have a lower current. And we can define this using a transconductance ratio, which is the amount of current versus voltage. It has a unit amp over V. And we can use this property to make an amplifier. So now let's take a look at some of the electrical characteristics and how it's differing from some of the common transistors we have on the market. So right here you see that we have three types of transistors. One is the vacuum tube, it's not a transistor. And then we have BJT and MOSFETs, which are the two most common type of transistors. The vacuum tube, as we just talked about, is a voltage-controlled current source. For the BJT, it's a current-controlled current source, while for MOSFET, it's similar to vacuum tube. It is also a voltage-controlled current source. Now let's see some of the common parameters. Test 1 is, in test 1, we are going to hold the input signal constant, which means we are going to hold the signal here constant, and we're going to vary the supply voltage, which means we're going to change the voltage at this point while holding this voltage constant. And observing its characteristics. As you can see that for a BJT and MOSFET, the characteristic of current versus the input signal reach a constant value at a threshold point. So after the threshold, the current that is flowing through the device really doesn't change that much, even if the voltage applied is greater, right? You see that voltage is changing for the BJT device is changing from 0.2 volts to 10 volts. However, the amount of current that is flowing through the BJT from the collector side to the emitter is staying around 15 milliamp. Now, for the vacuum tube is a different story. The vacuum tube, when we increase the supplied voltage from the anode to the cathode, we see that the amount of current that is flowing through from the anode to the cathode is actually increasing exponentially. So what this means is both BJT and MOSFET has current control capabilities, which means after a certain point, we can use it as a current source because the current doesn't change much, even the voltage changes. However, for a vacuum tube, we cannot use it as a current source because with the change of supply voltage, its current changes. The next test we're going to run is the exact opposite of the first test, where we will hold the supply voltage constant and change the input signal. This is how the device would normally be used as well. As you can see that for all the devices, no matter it's BJT, MOSFET, and vacuum tube, they all behave quite similarly. Roughly an exponential increase after a certain point. So, for example, for the BJT, after 0.7 volts, the current increases exponentially as the input signal increases. The difference is at the transconductance ratio, which defines how well the device can amplify the signal. For vacuum tube and MOSFETs, they all have a common transconductance value between, let's say, 2 millisiemens to 4 millisiemens. Obviously, depending on different device and how you bias it, it's going to change, but that's some of the common values. However, for the BJT, we can easily reach 50 to 20 times higher the transconductance ratio in comparison to MOSFETs and vacuum tubes. One thing I have to point out here is if you are actually able to calculate the transconductance ratio of MOSFET based on my number here, is going to give you a much higher number than 2 milliamp, 2 millisiemens. The reason is the data I'm using here is for a power MOSFET. It's this one right here, which has a really high width to length ratio. However, if you are using MOSFET for IC designs, this is going to be the common value. For BJT, you may remember that it is a current control current source. So why do we have a transconductance ratio which only a voltage control current source has? The reason is we're assuming that we're using the pi model, which means that we define the voltage to current relationship between the base and the emitter by R pi. And the voltage across R pi is going to define how much current is going to be controlled. And this allows us to calculate a transconductance ratio. Now, let's build a simple amplifier using the vacuum tube. The first one that came out of my head is just by putting a resistor on the anode and bias it with the 300 volt DC source. This design can work as an amplifier, but it's not very good. The reason is if you remember that the vacuum tube cannot be used as a current source. So when the voltage on the anode changes here, which is a V out, which will definitely change, the current changes as well. Unlike for BJT and MOSFETs, they don't change too much when the voltage on the drain of a MOSFET and the collector of a BJT change. This means the input voltage to output current ratio for a vacuum tube is not dependent on GM only, and this equation would not be true anymore. Instead, we have to consider the effect of current change when V out changes. This is an undesirable effect because it will create non-linearities. And we all love linear circuits. A better design would be using a transformer. Now, depending on how this transformer is constructed, we can have a much lower impedance on the transformer versus this resistor, which means that the voltage at this junction will much more close to 300 volts. And will stay there for a very constant value. And that means we will have a roughly more constant GM. So now let's talk about some of the drawbacks for a vacuum tube. The first one is we just talked about the IAC, which is the current from the anode to the cathode, will change depending on the voltage, which introduces a nonlinearity. It is very large in comparison to a transistor. We need to heat up the cathode in order to allow it to work, which requires power. And if you remember from the chart, the device needs to be biased at a very high voltage. And for BJT and MOSFETs, they can operate in the range of, let's say, 1 volt, 3 volts, right? And this high voltage is not very friendly because now you have to take special considerations into the design. So because of those drawbacks, vacuum tube has fall out of favor in comparison to other devices such as BJT and MOSFETs. I hope you learned something from this video, and see you next time. Bye.